Okay, so in this video we're going to start talking about the gravitational force. This unit that we're on right now is called Force Laws, and it covers the four fundamental forces of the universe. There's only four of them, but we're going to spend most of our time talking about gravity and the electrical force. Okay, and so in this video we're going to start with the gravitational force. And the force of gravity is a force that most people are familiar with because, well, that's what makes you fall down. Okay, when you drop a rock, or a piece of paper, that's what makes it fall towards the ground. The gravitational force is a force which exists everywhere in the universe. Okay, there's no place in the universe that doesn't have at least some gravitational force there. Contrary to what some people might have told you in the past, there is in fact gravity in space. Okay, and in fact, gravity is responsible for the orbits of the planet going around the sun, and the moon orbits the Earth because of gravity. The solar system orbits around the galaxy. The galaxy orbits around the universe, and so on. What holds all the stars together in the in the galaxy is in fact gravity. Okay, and so there is gravity in space. There's gravity everywhere. And in case you didn't know, gravity is also responsible for the tides in the ocean, things being pulled towards the ground, etc. And so one of the people in history who had the biggest contributions to our understanding of gravity was Isaac Newton, who you might know from Newton's laws of motion. Okay, and so Newton had three laws of motion, and we've talked about those last semester. But he actually had a fourth law, which is Newton's law of gravitation. Okay, I say his fourth law, that's not the official name, but he had the other three laws now. This one is, the fourth one, I guess. Okay, and so Newton's law of gravitation is an equation, and it's an equation that allows you to understand a little something about gravity. Okay, and so on the next slide you'll see the equation, and we'll talk about some properties of this gravitational force. Okay, so here is Newton's law of gravitation. According to Newton, all objects which possess mass, and so it's mass that gives rise to gravity, attract all other objects which possess mass with a gravitational force. Notice that the force of gravity is always attractive. Okay, attractive means things are being pulled together. Okay, and so some forces like the magnetic force or the electric force can be repulsive. If you've ever played with two magnets and you felt them push apart, you felt a repulsive force before. The gravitational force is always attractive. Okay, the second thing I want to point out is the property that gives rise to gravitation is mass, and all objects with mass attract all other objects in the universe that have mass with a gravitational force. Okay, now here's what Newton's law of gravitation looks like. I have the equation typed out here, but let me write it a little bit bigger so you can see. So Fg is the gravitational force. We've seen that before. We've seen force of gravity before. But the equation for force of gravity that we've seen before looks something like this. Fg equals mg. Okay, now this equation is only an approximation, and it's only an approximation close to the surface of a planet. The equation we're about to see is valid everywhere in the universe. Okay, so that's why this is also called the universal law of gravitation, because it applies everywhere in the universe. Okay, so this equation, the Fg equals mg equation, this is like the baby version, and what we're seeing now is the grown-up version. Okay, so Newton's law of gravitation says that the force of gravity between two objects is equal to g, that is a capital G, not a lowercase g. G is a constant that is called the gravitational constant. Gravitational constant. And the value of that constant is approximately 6.67 times 10 to the power negative 11. Okay, and so anytime you're using this equation to calculate the force of gravity, g is always the same value, 6.67 times 10 to the negative 11. That's why we started off talking about scientific notation, because when you're using this equation, obviously you have to multiply by this number that is in scientific notation. Okay, and so force of gravity is equal to g times m1 times m2. m1 and m2 are the masses in kilograms of the two objects that you're talking about, divided by our squared. Okay, now everyone knows m1 and m2 are mass. R is not for radius, but R is the distance in meters, because distance is meters, between mass 1 and mass 2. And of course, force of gravity is measured in newtons. The units for big G, the gravitational constant, you don't need to worry about those. Mass, of course, is measured in kilograms, and then R, that's the distance between mass 1 and mass 2, that is measured in meters. Okay, so make sure you add this to your notes so you know what everything in the in Newton's law of gravitation represents, because there's only two equations in this unit, and this is one of them. Okay, so pause there, make sure you add this to your notes. Okay, so we'll come back to doing calculations with this in a second, but let's talk about some implications of this Newton's law of gravitation first. Okay, so first of all, I said this before, but the gravitational force is always attractive. Okay, mass always attracts other mass. Second of all, if you look at the equation, let me make it a little bit bigger. We have mass 1 times mass 2 on the top. That means that the bigger the masses are, the bigger the gravitational force. Because if you think, if you're multiplying by mass, if mass is a bigger number, you're going to get a bigger answer. Okay, so the bigger the masses, the bigger the gravitational force. And that probably is obvious to most of you. Okay, the third property I want to point out is that the greater the distances between the two masses, the smaller the gravitational force. Okay, and so if you have two objects, the farther away they get from each other, the weaker that gravitational force gets. And the reason that is if you look at the equation, notice that we're dividing by r squared. And so if r is the distance between mass 1 and mass 2, if r becomes a bigger number, we all know if you divide by a bigger number, you get a smaller answer. Okay, and so the greater the distances between the two masses, the smaller the gravitational force. Okay, so let's do a simple concept example. Let's say you have a rocket ship, and the rocket ship blasts off up into the sky. The first question we're asked here is, how does the gravitational force on a rocket ship change as the rocket flies higher? Okay, so I want you to think about that and see if you can answer that question. Okay, so based off of what we just talked about in the last slide, the gravitational force on a rocket ship will decrease as the rocket flies higher. Now, why will it decrease? Here, when you think of Newton's law of gravitation, the two masses, or the two objects you're talking about, are the rocket ship and the Earth. Okay, so if the rocket ship is going up into the air, that means it's getting farther away from the Earth. And the bigger the distance, the weaker the gravitational force. Okay, distance gets bigger, force gets smaller, and so the gravitational force on a rocket ship is going to decrease as the rocket flies higher because the rocket is getting farther from the Earth. Okay, now take a look at the second question and see if you can answer this. How would the gravitational force on the rocket change if its mass decreased? Okay, and so the answer to that is the gravitational force on the rocket will decrease if its mass decreases. Okay, now why is that? Well, because again, if you think of the equation, we have g times m1 times m2 divided by r squared. So if one of the masses, or both of the masses get smaller, that means you're multiplying by a smaller number. That means the gravitational force is also going to get weaker. By the way, you might ask, why would the gravitational force on the rocket change? Why would the mass of the rocket change? Because as the rocket goes up into the sky, it's using up its fuel, it's burning its fuel, and so that's why the mass of the rocket would decrease. Okay, so rocket going up into the sky, the gravitational force is going to get weaker, both for two reasons, both because it's going higher and also because its mass is becoming less. Okay, so pause it there and make sure you understand that concept before we move on to the next concept example. Okay, concept example number 2. It says Jupiter, the 5th planet from the Sun, has a mass of 1.9 times 10 to the 27 kilograms. Neptune, the 7th planet from the Sun, has a mass of 1 times 10 to the 26 kilograms. Which of the following statements must be true? Okay, so there's 3 statements here. I want you to read those statements and figure out what is the answer to this question. Which of the following statements must be true? Okay, so try to answer that now. Okay, so statement 1 says the Sun's gravitational force on Jupiter is stronger than on Neptune because Jupiter is more massive. Okay, so let's see if that's true. Does Jupiter have a higher mass than Neptune? Okay, well, 1.9 times 10 to the 27 is a bigger number than 1.0 times 10 to the 26 because the exponent is bigger. Okay, we talked about that in the last video for scientific notation. The bigger the exponent, the bigger the number. Okay, so that is a true statement that the gravitational force is stronger because Jupiter has more mass. Okay, so 1 is a true statement. 2 says the Sun's gravitational force on Jupiter is stronger than on Neptune because Jupiter is closer to the Sun. So think about that. Jupiter is the 5th planet. Okay, so Neptune is the 7th planet. It is closer to the Sun, but does that mean that the gravitational force is stronger? Okay, yes, it does. We talked about this before, but one of the properties of the gravitational force is the smaller the distance, the bigger the force, or the bigger the distance, the weaker the force. So because Jupiter is closer, the gravitational force is also stronger. Okay, 3 says the Sun's gravitational force on Jupiter is weaker than on Neptune because Jupiter is closer to the Sun. That does not make sense, so the correct answer to this question should be B. Both statements 1 and 2 are correct. Okay, so now we're going to do some basic calculation questions using Newton's law of gravitation. Okay, so I will do one for you, and then you can try to do the next one on your own. So this question says, calculate the gravitational force between 2 students sitting 0.4 meters apart. The mass of student 1 is 60 kilograms, and the mass of student 2 is 85 kilograms. Okay, so let's say you're sitting next to somebody in class. You're about 0.4 meters apart. The two of you are attracted to each other because of the gravitational force. Okay, Newton's law of gravitation lets you calculate the size of this force. Okay, so Newton's law of gravitation, the equation is Fg equals g times m1 times m2 divided by r squared. As always, we want to identify our givens. Okay, so the distance between the two masses is 0.4 meters, so that's going to be r. Mass 1 is 60 kilograms, although honestly it doesn't matter which one is mass 1, which one is mass 2, it makes no difference. The mass of student 2 is 85 kilograms, so that's going to be mass 2. And so in my calculator, here's what I'm going to type in. 6.67 times 10 to the negative 11. Remember, that is the value for the gravitational constant. That's always the value for the gravitational constant. 6.67 times 10 to the negative 11. That's g, times mass 1, which is 60, times mass 2, which is 85. And then I want to divide by the distance squared. So 0.4 squared. And so I'm going to type into my calculator just like this. Okay, if you type it in correctly, and please make sure that you use parentheses around everything so that you don't accidentally make a math mistake. Okay, remember you can use the double E function for scientific notation, or you can just write out times 10 to the power negative 11. That's fine, either one is fine. My personal preference, you can do this or not, but my personal preference is to multiply everything on the top, hit enter, and then divide by 0.4 squared, just so I don't make a math mistake. But you can do whatever you want. If you do this correctly, okay, and I would try plugging it into the calculator now, the answer you should get is 2.13 times 10 to the power negative 6. Or if your calculator gives that to you as a decimal, that would be 0.00000213. Okay, of course, both of those are the same. And the unit for that is newtons, because that is the unit for force. Okay, so either of those would be fine. Obviously, it's easier to type it in scientific notation, but if you do type it in scientific notation, make sure you use a lowercase e. So if you were putting this answer into Canvas, you would write 2.13 e negative 6. Okay, now the question also says, why don't you notice this force? Well, that's because this is a really small number, right? Times 10 to the negative 6, look how small that decimal is. Okay, just to give you an idea, like the weight of an apple, if you just imagine like holding an apple in your hand, that's about 1 Newton. This is like literally like a million times smaller than that. Okay, so there is a force of attraction between you and the student next to you, but it's so small that you don't notice it. Okay, because it's too weak. Okay, so the force of gravity is there, but it's so small that it's not really detectable. Okay, really, you don't really notice the force of gravity unless the masses involved are really big or the distances involved are very small. Okay, so pause it there if you need to look at that some more. Okay, so I want you to try to do this calculation on your own. This question says, calculate the gravitational force between the Sun, which has a mass of 2.0 times 10 to the 30 kilograms, and Pluto, which has a mass of 3.3 times 10 to the 23 kilograms. The distance between the Sun and Pluto is around 5.9 times 10 to the 12 meters. Okay, notice that now we have a lot of numbers in scientific notation. Please make sure when you're putting this into your calculator, you put parentheses around everything. Okay, so I want you to try to do calculation example 2 on your own now, and you can check your answer in just a minute. Okay, so here's what your setup should have looked like. You have Newton's law of gravitation, G, m1, m2 divided by r squared. You plug in G, the gravitational constant, that's 6.67 times 10 to the negative 11. You multiply by mass 1. Again, it doesn't really matter which one is mass 1 and which one is mass 2, but just because they give us this one first, I'll make this one mass 1, and the other one can be mass 2. So I multiply by 2.0 times 10 to the power 30. Notice how I have parentheses around everything, and then I multiply by mass 2, which is 3.3 times 10 to the power 23. I divide by the distance squared. Please don't forget to put the square, and also don't forget to put the square on the bottom. It's 5.9 times 10 to the 12. Put the squared on the outside of the parentheses. So it's this number, and then the squared goes on the outside of the parentheses, and then you hit enter. If you plugged it into the calculator correctly, here's what you should get. Okay, so I'm just typing it into my calculator right now. So times 10 to the 23. Okay, and you should probably get a number that is also in scientific notation, just because this number is going to be pretty big. The number I get in my calculator comes out to be about 1.26 times 10 to the power 18 newtons. Okay, so that is how you should, or that's what the answer should be for this question. And the second question says, how do you think this force compares to the force between the Sun and the Earth? Well, Pluto's farther away, and also Pluto's like the smallest planet. I mean, it's not even a planet anymore, it's a dwarf planet. Okay, so because Pluto is farther, plus it's got less mass, the force of gravity on Pluto is going to be way, way, way less than the force of gravity between the Sun and the Earth. Okay, so pause there, make sure you understand how that calculation works. Okay, the last thing I want to take a look at in this video is specifically how the gravitational force changes with distance. Now we know that the bigger the distance, the smaller the gravitational force, but there's a specific shape to this type of graph, and this is called an inverse square graph. Okay, the reason it's called an inverse square graph is because if you think like the equation, you have force of gravity equals g times mass 1 times mass 2 divided by distance squared. Because distance squared is on the bottom, this is called an inverse squared graph. At the beginning of the year, we talked about like linear graphs, we talked about like quadratic graphs, and we talked about inverse graphs. Okay, so an inverse graph is very similar to an inverse square graph, and it has this shape. Notice there how you have like asymptotes here and here where it never actually touches the axis. Okay, so the gravitational force gets weaker as the distance between the two masses increases. Okay, and so we talked about that before, but this is basically just seeing that same concept like in a graph. Okay, so make sure you understand that relationship and make sure you understand how that would look like graphically if you were to make a graph of gravitational force versus distance. Okay, so in this video we talked about Newton's law of gravitation. We solved some concept examples with Newton's law of gravitation. We also did some very basic calculation questions with Newton's law of gravitation. In the next video, we will finish up talking about gravitation and then probably do a CER involving Newton's law of gravitation, probably just like involving very basic calculations. The most important thing is that you understand the concepts involved and that you're able to do basic calculations with the equation. As always, please let me know if you have any questions, and I'll see you guys in the next video.